Well, welcome. This topic is near and dear to my heart. I got very sensitized to valve sensitivity early in my career because I started out specializing in pH control. And we'll see for pH control systems with steep titration curves, you amplify any sort of uh, resolution or stiction or backlash you get from a control valve, and you need extraordinary rangeability in the control valve as well, and all of that is actually interrelated. And then I also specialized in compressive surge control, and there you need especially fast control valves that can stroke in a second. And so I got into understanding how valves need to be very precise and very fast. But we are going to go ahead and look at how that affects our overall view of what we want to do. Well, this is me, and you know me by now. I'm pretty sure there's a couple of key links here that can reveal what I've been doing for Control Magazine for the last 10 years, and also for ISA and the mentor program for the last 5 years. The top 10 things you don't want to hear from a valve supplier. I went out for bids and found the cheapest possible valves. These valves have been extensively used in packaged equipment. These valves have such tight shutoff, I dare you to try and open them. You can standardize on these valves for isolation and sequences. And you can get all the flow you need when the valve is just 10% open. Why do you want to know the valve response time? We have quick opening trim. Thanks to my 1969 guidelines based on Nyquist plots, I was able to omit positioners. We don't need to know the piping system. All I need is the available pressure drop at the design flow. What do you mean by installed flow characteristic? Well, some of these things may not seem all that funny, but hopefully after we go through this and you look back at this, maybe it will be a little funnier. Alerts. The common mistakes made today, and this may seem like, wow, really? These sound like good things to be doing. So it is something we're going to emphasize here as being important. And common mistakes is a focus on minimizing leakage and maximizing capacity, minimizing valve to system pressure drop ratio, and minimizing costs. These things may all seem to be important and good things, but we'll see how, if they are the primary objectives, they can lead to some very bad applications. Watch-outs. Things that are commonly noticed is that actuators are sized for loose packing and for room temperature. So if you have elevated temperatures and you've tightened up the packing, your actuator size is not large enough, and we really advocate actuators just being sized more than what may be initially thought of as being what's appropriate by the supplier. Also, actuators sometimes are sized so that they don't really give you the smallest resolution or and best response. So you need to realize that sometimes what they're doing is trying to save you money, and that may appear to be useful, but it has some severe consequences. The other thing to realize, when you specify a resolution in Deadband, which is kind of rarely done but should be done, and you do that, like I have done for pH applications, they will do those tests at 40% or so, greater than 40%, so that they're far away from the seat of the valve, so that they don't get into seat and seal friction. Also, they'll do the response time tests for steps that are not very small or not very large. And so they kind of get the best scenario in terms of the response time. Also, they do not indicate what the shaft windup and backlash might be, and it's not really measured and given as an alert to you. There is an error between the feedback stem and closure member that can be huge, and we'll see that is particularly a situation if we are getting into valves that were designed for minimizing leakage and maximizing capacity. And as a result of the error between this feedback stem and closure member, and that error could be as large as 8%, the positioner is being lied to, because what it gets as its information is the feedback stem measurement. And I've seen cases where it looked like, oh, the resolution and deadband was like only 0.5%, and when I looked at it in the shop and put a travel gauge indicator on the actual butterfly disc, it was not moving unless you made changes that were greater than 8%. So the positioner gave me all these statistics saying everything was wonderful, when in fact it was horrible, and that's due to an error between the feedback stem and the closure member. The closure member is the internal thing that's actually throttling the flow. It could be a disc, it could be a ball for a rotary valve, or it could be a plug for a sliding stem valve. The other thing is boosters being used instead of positioners. There was a theoretical study done way back in the 1960s, I think, or 70s, that said, if you got a fast loop, you should be using a booster instead of a positioner. And I found out the hard way doing that is a disaster, and that you can get into unstable conditions due to something that's a little complicated there, but it's happened to me. I've demonstrated a number of times. There's some positive feedback going on there, and without the positioner adding in this negative feedback, you can get into real trouble with the valve actually slamming shut on you when it should be opening for, say, surge control. Anyway, very important that you never omit a positioner, and even on a fast loop. And we'll see how on a fast loop we can use a booster by putting it on the positioner output. And the other thing that's happening, and I didn't realize it, but the integral action in a positioner is being turned on in modern day positioners. When we had positioners up until the 1990s, they were proportional controllers, high gain controllers, like gains of 100 to 200. No integral action. Now with a smart positioner, you can have integral action, and it's being turned on as a default because if you make a little step test, it may look better in terms of eliminating an offset eventually by having integral action, but it's very detrimental in terms of creating limit cycles, which we'll get into, and also causing you to back off on the gain in the positioner, which is really what you most want to maximize to get the fastest response. So let's compare sliding stem versus rotary valves. Sliding stem valves, there's no translation of motion. We're not trying to go from vertical to rotation, vertical action of from the actuator to rotation of a disc or ball. So we don't have to worry about this backlash and stem feedback error that we would get in rotary valves. There's less seating friction in general. And there's more choices of flow characteristics. By the way, there is a less chance of an oversizing because these valves through the these valves by flowing through that orifice around the plug is just not wide open like it could be in a rotary valve. Then if we consider rotary valves, they're a lower cost, and the cost saving increases with the square of the size, so that's very attractive. So you get into very large valves, and of course you're probably going to have to move to a rotary valve unless you have a very good case that you need the benefits of a sliding stem valve. It gives you more capacity. There's less abrasion and plugging from solids, less coating of the stem from sticky fluids, and less stagnation by elimination of crevices. And this is critical for sanitary operation, beverage, food, and pharmaceutical processes, and is critical to prevent polymerization. I read into this in plants that use hydrogen cyanide and acrolein because of these process chemicals, which are very highly reactive, accumulated in a crevice, they would polymerize, and it would be a very high exothermic reaction, and that would just take off and be very dangerous. And so for hydrogen cyanides and acrolein, we had to be very careful not to have any crevices. So it became a real safety issue. However, we need to be aware of the fact that we can create limit cycles from resolution and deadband. And a limit cycle is an oscillation that has a constant amplitude. So that's how you can kind of discern it from other oscillations that you might have in your control loop. The limit cycle from Stiction occurs if you have just one or more integrators in the system. And in the system, I mean, that could be as a result of being in the positioner in the process, like if you have a level loop, it's got an integrating process action, or of course, when you're looking at the PID controller, if you have integral action in PID controller. And if you have cascade control, you got to consider, all the PID controllers. So this is one of the reasons why you don't want integral action in your positioners, because right away, even if you're not changing the signal to it, you have Stiction there, you're going to get a limit cycle appearing in your actuator from the integrating action that was added to your positioner. Now what's interesting is the amplitude of the limit cycle is set by the process gain, and so there's really nothing you can do in terms of tuning to change that. However, you can affect the period of it, and so by increasing the controller gain, you can reduce the period of this limit cycle, and that may be beneficial in terms of then other volumes downstream being able to better filter out an oscillation by it having a faster period. The limit cycle from Backlash and Deadband for two or more integrators in the system. And now we see that the Backlash, B sub V, which is really a deadband, the amplitude from that is inversely proportional to the controller gain. So as we increase the controller gain, we can reduce the amplitude. Oh, and by the way, it only occurs if there's two or more integrators. So again, if you consider a flow loop, if you don't put integral action in the positioner and you just have integral action in the PID, you're not going to get a limit cycle from Backlash. Now you consider a level loop and you got integrating action in the process, and then you have integrating action in the PID controller. You got two or more integrators, and then you're going to have a limit cycle. But here you can see that you can increase the controller gain and reduce the amplitude. And also by increasing the controller gain, you can again decrease the period of the oscillation. And I should have put up this definition and nomenclature here that shows, although it's not that difficult maybe to decipher. Now there's some actual test results for ball valves with metal seals, diaphragm actuators, and standard positioners. And one has a good ball valve designed for throttling, and the other one has a poor valve designed for throttling. And we have the input signal as a dashed line, the actuator position as a green line, and the flow rate as a red line. And we're really nice having that flow rate. It's a low noise, a pretty responsive flow rate measurement, and so we can see if the flow is actually changing. And for 0.5% steps with a good ball valve design, we are seeing some changes in both the feedback stem position, that's the green response, and also, most importantly, in the red, which is the flow measurement. However, if we go down to the pore valve design for throttling, we see that there is kind of a movement of actuator position, but there is no change in flow rate. So again, this is what I mentioned before, that there's a situation of lying going on to the positioner. It doesn't even realize fully that how bad the lack of response is. And even as you get into larger step sizes, you start to see more of a response in actuator position. And then even at 2%, you see it maybe even more consistently, but there isn't always a flow response. So again, you're maybe oblivious to the fact that you are really not getting flow changes unless you have a good flow measurement that is telling you what the real situation is. And maintenance tests, which is what we used to do many years ago, of making 25% or 50% steps, will not detect backlash and stiction, and all valves look good except for stroking time for 10% or larger steps. So the key, again, if you're going to figure out what's really going on, you need to make small step sizes, and we'll get into how small is small. Now, if you go to rotary valves, one of the problem is you tend to go with piston actuators, and the piston actuators introduce some concerns. One is right off the bat, the sensitivity of a piston is probably 1% versus being 0.1% for a diaphragm actuator. And then you have some problematic connections that are offered here. And the top one is called a link arm connection, and you've got these pins here, and you've got backlash and deadband being introduced by those pins. And then in the middle one, what you have is a rack and pinion connection, and you have a pretty significant slide bearing friction, and then you've got these gear teeth that introduce a resolution limit as you're making changes. And then the last one is probably the worst, where you have a Scotch yoke connection, and you've got that slot there. And whenever you have a slot there, that introduces significant backlash and creates deadband. There's also problems with the piston wearing at seal out and creating additional problems, and also there could be a shaft windup going on that and an error in what is seen as an actuator stem position versus what is actually happening in the valve. So if the application permits, a sliding stem glow valve generally have the least backlash and stiction and a wider throttling range with a good characteristic, but may not be suitable for large sizes or slurries. And, you know, for some situations we already mentioned where there could be some sticky fluids that you have to deal with that could coat the stem, which then presents additional packing friction. Diaphragm actuators generally have a resolution of 0.1% versus the 1% for pistons. But, you know, you get into a limit like how much actuator thrust can you get out of that, and you know, and the problem is that the traditional diaphragm, the maximum air pressure was 30 psig, whereas with a high pressure diaphragm, the maximum air pressure is now 90 psig. So now you can use a diaphragm actuator for handling much larger valves or much larger pressure drops, and so you can get the better control offered by the diaphragm actuator. Well, way back when, maybe a few decades ago, there was an article by some very knowledgeable people saying, "Oh, you want to use pistons," and they were unaware of this whole thing about resolution and stiction limitations and linkages and causing backlash. And so, it is a problem that's really not understood very well, and so my job is to try and provide the knowledge here. It's going to be a lot to absorb here, but we'll have a recording. Now, if you get into sanitary operation, there is still a sliding stem valve. It's not very well known, that enables precise low flow, and it actually would be laminar flow to the third power stem position, which introduces a huge nonlinearity, which you can take care of by signal characterization. The rangeability, though, is incredible due to the precision. I mean, you can change in the third power of stem position. You have a rangeability of maybe 15,000 to 1 or something. It's incredible. But anyway, it is for sanitary flow, low flow applications. If you have a rotary valve, what we would prefer is a spline short shaft connection for minimal windup and backlash, and so that we can get from a rotary valve something that's approaching what we can get from a sliding valve in terms of precision of response, and not have the positioner hopefully being lied to. So there's dramatically less windup and backlash than pinned or keyed connections. So this spline, you'll see these splines, and it's pretty dramatic, the improvement. Here, a segmented V-notch ball reduces torque, reduces friction, improves flow characteristic at low flow, and the spline shaft reduces backlash. Just saying that you have a V-notch ball doesn't mean it's going to be this particular valve. I found out when I was trying not to say valve names, but said, hey, you should be using a V-notch ball. The guy came back later. Fortunately, he did come back by email and say, I don't agree with you. I looked at the flow characteristic, and for my V-notch ball, when I have essentially no flow until I open about 15 to 20%, and then the flow jumps way up. And so I'm not sure what valve he had exactly, but it was really an on-off valve and wasn't a throttling valve. So I've gone to saying, well, is the original purpose of that valve throttling, or was it on-off or isolation, as determining whether it really is going to provide what we need in terms of flow characteristics and in terms of being a precise response to meet particularly our small changes in signal and position. There's a contoured disc that reduces torque, which reduces friction and improves flow characteristic at low flow. And again, the spline shaft reduces backlash. The teeth reduces noise on the disc. Now we're going to look at what I talked about, backlash. But here we can see, what does it really mean? Whenever we reverse directions, we have to go through a deadband associated with the backlash, and it tends to be worse near the closed position. And here I also show some stiction near the closed position, because I like to keep reminding people that the stiction is greatest near the closed position, particularly for rotary valves. And that's why suppliers, unless you specify otherwise, will not test to give you their deadband and resolution limits near the closed position. And here you show in the wide open here how much smaller the deadband is. And again, it's how much of a signal reversal do you have to occur before it starts to move when you change the direction of the signal. Now, often it's confused by somebody saying, oh, well, what is a hysteresis? Technically, the hysteresis is not that deadband. There is but it's this bowing of the curve. And while that may be important in some other mechanical type components, it's usually not an issue here in actuators. And so I've exaggerated it to show the effect. And so one of the problems here, if you say, oh, I want the hysteresis to be less than 0.2%, they can say it is, even though it could have a huge backlash and deadband, because the official definition of hysteresis is this bowing, which is a rather minimal effect. So you need to be precise in your terms to make sure you don't get into trouble. Resolution limit is typically result from stick slip, and here if you have a continuously ramping signal, but what you're seeing is it sticks and then it slips, so you get a staircase. And the resolution varies from 0.1% to actually 10%, particularly some valves that have high friction due to tight shut-off near the closed position. Okay, when you need to make a valve fast, you should put a booster with bypass on the output of the positioner. You never omit the positioner because of the very dangerous situation. So despite age-old guidelines, as I've noted up here in red, never replace a positioner with a volume booster. It's potentially unsafe. Then please turn off the integral action in the positioner that has been enabled as a default by the supplier. And then you got to look at the air supply line. Must be short and large and dedicated to the booster. This air supply should not be shared with a positioner and other users of the air, so to ensure there's no dip and restriction in booster airflow. One thing really important, particularly for a certain manufacturer, but in general, look for the lowest friction packing. And it may turn out that that ultra low friction packing, ULF here, actually has a pretty high temperature rating. And so, you know, you're thinking of high temperature trim, you might think normally of going to graphite. What is much better is to go to this ultra low friction packing. And it will actually meet your temperature rating. And furthermore, I think what I understand is the friction doesn't change that much with temperature. So when you do a test in a laboratory or shop, it's going to be the same results pretty much as when you have it in line and say you're operating at a higher temperature. And one thing you got to realize is to open the bypass just enough to ensure a non-oscillatory fast response, because if you don't do that, the initial thing is to be some very high frequency oscillations, like I think it may be around 1 cycle per second. It's very noticeable if you have it there in the shop. Of course, you want to try this out in the shop, and then you open it to stop that. And you maybe open it a little bit further so that you make sure it doesn't ever start again. And it's a situation where if you open it too much, you've kind of lost the advantage of the booster because you're bypassing it. But to be conservative, maybe you want to open it a little more than what is initially required to stop the oscillating response. And of course, you must functionally test everything before commissioning. Here's an example of a volume booster that has a built-in adjustable bypass needle valve. So you wouldn't have to pipe a separate bypass valve around the booster. So let's look at some tests here and how we can deal with what we have in terms of backlash and stiction by how we tune the PID and what features might use in the PID. So here we can identify what the backlash deadband is by making small step changes in the signal, and that's that little black staircase there. And you can see that the flow, this is the flow loop, we're fortunate that the flow loop is actually responding until we reverse direction. Now we reverse direction and we notice the flow loop doesn't see any change in flow. And the amount of signal change, total signal change, when we sum up all those little steps that we need is the deadband, and we call that lost motion. You know, until the signal changes by that much upon reversal, we're not going to see the flow actually change direction. So let's see the consequences on flow loop operation. 10% load upset, 0 and 10% backlash, and we're going to show what the effect is for 0.2 and a 0.05 PID gain. So here with a 0.2 gain, what we see is a pretty reasonable response. Well, actually, this is 0% backlash, so you know, we're just comparing here to that with 10% backlash, and we notice that there's some deterioration, but it's a reasonable response here. And so you need to look at the top of the heading here that shows you the test situations, the conditions. And so we started out here with 0% backlash and 0.2 gain, and then we went to 10% backlash and 0.2 gain, and deteriorated a little bit. And then if we detune the PID for whatever reason, we see that now we're seeing a significant deterioration in the response. And why? Because backlash, that deadband actually adds dead time. And if your controller output is changing at a slower rate due to a disturbance, it takes more time to get through the deadband. And so we've added dead time to the control loop, and we've got a much slower recovery from the lower PID gain. So I put that in big, the conclusion in big green text here at the bottom of the test case. Now let's look at a level loop and a 10% load response with 10% backlash. And now here we have an integrator in the process, and we have integrator turned on in the level controller. And so we've got two integrators. And so the result of having two integrators, we're going to have a limit cycle. And we see here that we can, though, affect the period and the amplitude by changing the gain. Notice with this first situation you have here, very initially, and we don't see very much of it because I'm trying to show all three conditions here. The gain is 4.4. And by the way, the external reset is turned off. That's a function we'll get into and talk about and see the effect of. And then we just show increasing the gain, and as a result of increasing the gain, we see that we actually reduced the amplitude of the oscillation and made the period faster. Now, you look at this and you say, oh my gosh, the loop is oscillating. What do I need to do? Well, you know, you may think, well, I need to decrease the gain of the PID. Well, this is what happens when you went to a 0.88 PID gain. So, you know, for this last test case, we see very large amplitude, very slow oscillations. And this is much more problematic because you got a bigger amplitude to filter out by your volumes, and the fact that it's slower, you're not getting as much filtering action by your volumes downstream, and it becomes much more of an issue. And here you thought maybe you're doing the right thing by decreasing the PID gain because you have an oscillation. Here we show what you can achieve by simply turning on external reset feedback, and that's an option available in some PID controllers. So, you know, we have this case that we showed before of increasing the PID gain and how we were able to reduce the amplitude in the period. Now we say, well, let's go with a higher gain and let's turn on external reset feedback. And we know that we see that there is still kind of an oscillation, but I think eventually it may actually die out, but it is significantly reduced and almost to the point where it probably would disappear in the results of what else is going on in terms of level control. So simply turning on external reset feedback that tells the controller what the valve is actually doing. Now, this all depends on there being an accurate stem feedback and therefore readback measurement of what the valve is actually doing. If you have the positioner being lied to, like would be the case in a rotary valve, there isn't going to be any benefit from turning on external reset feedback. Now let's take a look at Stiction that's creating a resolution limit, and we see for the same staircase of tiny step changes, we see that there is a step change occurring and a staircase occurring that is much larger than those little tiny steps we're doing in the signal that is in the actual flow response. And we don't have any deadband here, so it's really just how much accumulation of steps in the same direction is required for you to see a flow change. So it doesn't depend whether you're changing direction or not, like there was with Backlash. It's always there. So let's look at a closed flow loop, and we look at 6% Stiction and again, a more PID gain, and we see that we have a limit cycle, and if we decrease the PID gain, we still have the same amplitude of the limit cycle, but we have made the period worse. Now, if we turn on external reset, we can see that we can actually stop the limit cycle from Stiction for the flow loop, but there's an offset here of the flow from the set point, and that's just a natural occurrence. Now, instead of turning on external reset feedback, you could enable integral deadband, but now you've got to choose an amplitude that corresponds to what you think is the deviation around set point that corresponds to the deadband. That's that requires some knowledge and tuning maybe, whereas here we're just simply turning on external or reset feedback. So the lower PID gain increases the limit cycle period, and external reset feedback stops the cycle but with an offset. That was with the flow loop. Level loop here with 6% Stiction, we see that basically we have an oscillation, and the oscillation reduces the amplitude and the period, and I have to check this because I think I'm a little bit unsure about some of this, but I think this is right. Because it isn't adding an integration in the process. Those equations I presented previously was for a self-regulating process, and so here we have an integration process, and we are going to see the effect of PID gain then on amplitude as well as period for Stiction. Okay, now something that's even more devious that I wasn't aware of is that the poor positioner designs. You can have positioners that really don't show up to be a problem unless you make small steps, and I mean by small steps that are smaller than 0.5%. And some really bad positions, maybe smaller than 1%, but many of them. It could be 0.5%, and so we see here that for these small step changes, 0.1%, we're seeing an increase in dead time to 40 seconds. Previously, it was less than a second. And if we reverse direction, it's like doubling to like 80 seconds, and incredible. And it's something. Just people didn't realize, but actually James Bell, who worked at Eastman, first identified this problem back in the 1990s. Anyway, it's an extremely devious thing, and so you really want a positioner, a modern positioner that is it's not the cheapest positioner. It's really a positioner designed to be able to respond to small step changes. So what are the consequences of that sort of positioner that doesn't respond well to small step changes. Well, here we see a flow loop, and boy, it just gets bizarre. We have these irregular cycling due to a variable dead time. And if we increase the gain, which is counterintuitive, we see all that messy cycling. It's not a limit cycle. It's just a messy cycling. We would say, oh, well, we got to reduce the gain. But if we increase the gain and increase the reset time, so you have less interval action, you actually do much better, and you can stop the cycling. And then if you turn on external reset feedback, provided you have an accurate stem feedback measurement, then you can actually get a pretty darn good response. Now let's look at the last scenario, and that's where you have a big valve, a large volume actuator, and so you got a large stroking time. And here we're looking at 0.6% per second slew rate. And so you see for big signal changes, there's a velocity limiting, rate limiting going on here to the slew rate limitations of a very big actuator. And that didn't have a booster put on it, say. So here we have a large actuator and 0.2 PID gain with the external reset off, and notice we get these kind of big oscillations on a load upset and very undesirable. Simply turning on external reset feedback, again, if you have a good stem feedback measurement, kills the oscillation because the PID recognizes, hey, the valve isn't really responding, and so I can't keep driving that interval action. Here, the same sort of situation for a level closed loop, larger step change, load step change, and very large actuator, and we're showing how we got these oscillations going on, and that we can stop them by just simply turning on external reset feedback. Now, what about the trim characteristic? What people don't really get into sufficiently is the effect of the ratio of the valve pressure drop to the system pressure drop. And so we have a linear trim here, where the inherent characteristic here is the blue. And so, it looks very nice, linear. But because we're very conscious on minimizing energy usage, we may be allocating a very small percentage of the total system drop to the valve. So we have frictional losses going on in the piping system, and we're saying, oh, well, we don't want to add more frictional losses in the control valve. We want to minimize that as much as possible. And so there's even been some statements, as shown way over here to the left, that why not allocate just less than or around 5% of the system drop as the valve drop. That way we can, save energy. And what we have then is the purple curve here, installed flow characteristic number 4, and what we've ended up with is a quick opening type of response, which is very detrimental to control. We normally don't want quick opening. There could be an exception in terms of some pressure or surge control, but we have to realize there's a loss in rangeability due to the steep slope, and that the backlash that we see from lost motion and the stiction we see some friction are going to translate to this very much larger amplitude due to the very steep slope here. And the traditional definitions of valve rangeability often do not take into, well, except for me, I guess, nobody takes into account the loss in rangeability due to backlash and stiction, which all depends upon how much it's amplified by the slope there of the installed flow characteristic near the closed position, where the stiction and backlash is the worst. So you see how you're better off with the red curve and maybe allocating about 12%, red curve. Actually, that would be 50%. Well, that might be too much to allocate. So maybe the black is a compromise here. Which is curve installed characteristic number 2, where you've allocated maybe about 25% of the system drop as your valve drop. Now, what happens to an equal percentage? Well, it actually becomes a little more linear as you allocate less of the system drop to the valve. So maybe it's not as quite as problematic. But look what happens here in terms of minimum flow. You're raising the minimum flow achieved, so you lose rangeability very significantly. So if you allocate only about 5% of your system drop as your valve drop, you really aren't getting much of a flow change or any flow change below 10% valve signal. Or I guess as shown here, maybe below 5% valve signal. There isn't much, if any, of a flow change. So you have that loss in rangeability due to a very flat slope. I became sensitized, as I mentioned, to valve resolution because look here at the pH. If you're on the flat part of the curve, hey, the oscillations don't really translate. The oscillation limit cycle here doesn't translate to much of a pH oscillation. So those people who are lucky to have a flat titration curve near their set point, hey, things are, okay. What is this big deal about minimizing valve resolution? But if you have operation on a steeper part of the curve, and this isn't as steep as it could be. If you had a strong acid, strong base, it is so steep here, it's like a vertical line. So this is not even the worst case scenario. But notice how you get this amplification here as you go to a higher pH where on the steeper part of the curve, probably around 7 pH is normally the steepest part of the curve, and you get a big amplification of the oscillation. And the oscillations could be due to non-ideal mixing, valve stiction, and backlash, or pressure fluctuations. So all of these things I became very sensitive to in dealing pH control. So what can you do? You can end up with a coarse and fine valve if you want to extend rangeability and make sure that you minimize oscillations when you need small flow changes. And I guess as Hector showed here, but as applied to pH control, you can have an integral-only valve position controller that's looking at the PID controller output for the pH controller that's manipulating a very small, fine valve, and it doesn't really need to see the actual position because we're just trying in general keep that small, fine valve in a good throttle range, say around between 20 and 80%. And we do that by positioning the large valve, and we don't want to position that very much or very quickly. So we use integral-only control, or maybe even more intelligently, a notch gain or nonlinear gain PID control that doesn't do much of a change in terms of positioning the coarse valve unless you get that fine valve to start to get out of a good throttle range, start to approach the closed position or the wide open position. But the tuning of that valve position controller, ZC 1-1, and Z in the ISA nomenclature is normally used for, I think, valve position. ZC speed of response must be slow, and tuning is difficult. And what you need to do is, particularly if there are big disturbances, is to add a feed forward so that you immediately position the big valve, because it's not going to be able to recognize that the small valve is ran out of its throttling range. Well, it'll recognize it, but it won't make the corrections needed quick enough. So a feed forward is very essential in this case. Now, you can use model predictive control to do the simultaneous adjustment, and you set up two control variables. One is, of course, pH, and you want that to be tight control, but then you want kind of a loose control for a control variable that is the requested position for the reagent valve. And you can see the model is very simple, so it's very easy to put in there. It's just a gain of 1, and that's all you need to do is enter a model for the control variable being a small valve position or requested position versus the requested position as being manipulated. And but now you need to actually do testing to get how the small valve and large valve affect the neutralizer pH. So it can be set up for rapid simultaneous throttling of a fine and coarse valve that addresses interaction, rangeability, and resolution issues. Coarse valve penalty on move, called move suppression by some suppliers, is increased for the manipulated variable, and fine valve position penalty on error is decreased, which is a control variable to reduce unnecessary movement of the coarse valve. And you can add disturbance variables that are acting like feed forward did for the PID. They can be readily added, and you'll get better dynamic compensation right out of the setup here, because it's with mild predictive control, you can add a disturbance variable and it'll do testing, and it will automatically identify the dynamics needed. Where to do it for PID control, it requires some special setup and understanding to get the feed-forward dynamics. So the lesson I've learned throughout my career has been I can explore, experiment, discover, and learn by the use of a virtual plant. You know, you can make changes and trial scenarios you can't do in a real plant. Yeah, and you don't want to do things in a real plant too. You really understand what the situation is and what you can do that would be beneficial. And so that's why I use dynamic simulation in a virtual plant, where you've simulated not only the process, but also you've simulated the PID and its features and tuning, and the automation system, in particular the valve. One of the things that's really been missing from virtual plants is the dynamic response of the control valve and the static response. Because I say static because people, you know, when they get into official definition of deadband, and maybe, yeah, I know deadband, they say that's static, but anyway, we're talking about valve response, and now I have objects created that enable me to have a variable backlash and stiction, so I can change it as a function of stem position, and I can increase it as you get closer to the seat. I can have a variable dead time that it shows you a positioner sensitivity. All positioners kind of lose some sensitivity for very small step changes, which shows up as an increase in dead time. So I can do that by writing to the dead time. And of course, you want to write to the time constant, and that's kind of a normal thing that you would get in any sort of filter block. And you want a variable velocity limit, so that you get in very large step changes, you see the slew rate effect in terms of what the valve, how fast the valve can actually position. So concluding remarks. A counterintuitive increase in PID gain may actually be helpful in most cases. Backlash and stiction increase dead time as the PID gain is decreased. If an oscillation is not decaying and period decreases as the PID gain decreases, the oscillation is most likely a limit cycle from backlash or a stiction. Tuning or true external reset feedback may stop oscillations if the readback of the actual ball disc or plug position is fast and precise. That's a big if in rotary valves, specifically if there was originally for on-off or isolation. A dramatic increase in PID reset time is helpful for positioner case. Due to backlash and stiction, they show up as a square wave in unfiltered flow. That's it. You know, that's a good way of recognizing it as well. If you see a square wave in the unfiltered flow, it's due to a limit cycle from backlash or stiction. Low noise, high rangeability flow measurement is extremely useful. It reveals and deals with backlash, poor positioner, lying valve, due to poor stem feedback, and a nonlinear valve gain. Backlash should not cause a limit cycle in just a flow loop. Single integrator if there's no integrating action in the positioner, but response for low PID gain has delayed slower oscillatory recovery. Oversized valve may increase PV amplitude of limit cycle from higher stiction by operation closer to seat or seal, and greater valve gain from the installed flow characteristic. Anyway, I didn't get a chance to discuss the fact that there's things that you can do with the signal, like give a kicker or put in a step size low limit or enable lead lag, say in your positioner to help deal with particularly backlash and deadband. Please, let's not go backwards. Instead, realize the value of the technological advances. You know, there's been a lot of improvements in control valves, and we need to recognize them and use them particularly where it's needed. And a key thing is to use on-off and isolation valves for sequences and safety instrument systems, SIS systems, and use low stiction and low backlash throttling valves with smart positioners for control loops. Many loops require both types of valves. If the size and process conditions permit, preferably use sliding stem glow valves with diaphragm actuators and ultra low friction packing. Make sure valve drop is at least 25% of maximum system drop. Make sure actuator is sized for 150% max torque and thrust. Please add the following requirements to the control valve specs, and this is a stretch because nobody's doing this, but this is what I want to see happen. It may not happen this year, but this is what should happen. Resolution and deadband, you ought to specify that, and you should specify what requirements are, minimum flow, and this is a range that I would seem as appropriate. You could say that it is less than 0.2%, or you could raise it on up to 0.5% if you don't need particularly tight control and don't have a high process gain. Stem position readback error must be less than the resolution so that you can actually see what's going on. For small steps, you want the 86% response time from 1 to 5 seconds. The 1 second probably corresponds to surge control. And the small step size, I would say, should be the resolution plus 0.1%. And this is region 3 in the ISA technical report that I'll give you the title for shortly. And for large step changes, 20% where you start to see slewing rate effects, you can maybe up the response time to say as large as 20 seconds if you don't really need a particularly fast valve, like as a temperature loop, and so it doesn't need that. And you're not probably going to make large changes anyway, but anyway. You don't need a large step response time. That's very fast. Valve gain for the installed flow characteristic. Make sure that's underlined there. Make sure it's just not the inherent. It doesn't change more than by a factor of 4, so it's the 0.5 to 2% flow per percent stroke. Make sure the minimum flow valve position in your sizing is greater than 5%, and if necessary, use a fine and coarse valve to achieve that. Both this and achieve your resolution and deadband requirements. And make sure the positioner tuning is overdamped but aggressive, high gain, no integral action. And this means for DVC, you enable travel control rather than pressure control. Because if you turn on pressure control in a digital valve controller or DVC, it automatically turns on integral action. So a lot of this was discussed in this ISA book, and most recently all these test results were discussed in this Control Magazine article. And at the bottom here, I have in purple the ISA standard for testing control valves and the technical report. You can view these online for free. By just using your ISA membership. If you don't have a password, you're going to have to get one created, but you can view them online now for free, and I encourage that. Although some of the standard and report need to be updated per what I found out here from my testing. Wow, that's a lot. And so if you're still there and you have some questions, feel free to ask them, or you can send me an email. Well, I'll send you a recording probably sometime next week. And thank you all for attending.